In this Sallen-Key differential filter amplifier topology that is implemented using 3 ideal op-amps, we want to see what is the relationship between the output voltage of the circuit as a function of the input voltage signal applied. To do this quickly, let's make the assumption that all the 3 op-amps are properly biased, meaning that the negative positive supply voltages are there correctly, so that op-amps are not saturated in linear region of operation. Therefore, effectively we are saying V positive equal to V negative. Basically, virtual short is valid for the op-amps. All op-amps are in linear region of operation. Okay, so let's name, let me just use a different color. So let's name this node as, for Vin, let's name here as V1 for positive terminal of this op-amp 1. Let's name this node as voltage V2, for op-amp number 2 for the positive terminal. Effectively, we are saying that Vn is equal to V1 minus V2. So that's the only thing I'm doing. The benefit of that is V1 appears here because of virtual short that says that the positive negative terminal should have the same voltage. Also, V2 appears here for the same reason at this node. One could say that voltage V1 observe a non-inverting amplifier. So easily in that sense, one can say this node at the output of this non-inverting amplifier has a voltage output which is 1 plus R1 over R2. So R1 over R2 times V1. I mean, it's easy to compute that. The moment you assume this is V1, there is a current flowing this way, and you can see that this V1 is just a voltage division with this node. And it's just a scale up of the voltage by the factor 1 plus R1 over R2. Okay, so with that in mind, let me just do a little cleanup so that it's not as busy looking. All right, so this is the scheme for this node. And now for V2, let's say we want to get to, let's name this as VA. So we want to get to VA, and to get to VA, it is another non-inverting amplifier, this op-amp 2 for voltage V2, and it is an inverting amplifier for voltage V1. So for this voltage via R1, R2 to VA, it's an inverting amplifier. But for V2 is a non-inverting amplifier. So using, effectively I can say like this. Let me change the color back to something that is better. So I can say, as easy as this, I can say from 1 plus, okay, so from 1 plus R1 over R2 V1, so from this node, which is this point, to VA is an inverting amplifier. And that means the gain is just negative R2 over R1. That's easy. From V2 to VA is a non-inverting amplifier. So from V2 to VA is a non-inverting amplifier. I mean, this is easy to obtain, but it would be redundant to do it because using KCL, you can easily write a KCL at this node and find the total gain. But what I'm trying to say out of this is effectively then using superposition, I can say effectively VA, this voltage, is the sum of the impact of this voltage and also this voltage. So one by one, what I can do is VA is negative R2 over R1 times this voltage. That's the meaning of inverting amplifier. 1 plus R1 over R2 times V1. So that's the effect of V1 in terms of its contribution to VA. Now, for the non-inverting contribution from V2 to VA, we have simply 1 plus R2 over R1 as expected. So it's 1 plus R2 over R1 times voltage V2 at the positive terminal. So that is as easy as voltage V2. If you simplify this, it's very interesting to notice that after you multiply negative R2 over R1 and distribute it inside this parentheses, you end up with this very interesting outcome, that it's 1 plus R2 over R1 times V2 minus V1, which effectively is negative Vin by definition of Vin and relation of Vin and V2 V1. So as a result, I can just say, because of this final outcome, I'm summarizing that VA is negative 1 plus R2 over R1 times Vn. So that's the meaning of the differential amplifier of this whole circuit. So this is literally a differential amplifier. So I would say differential amplifier gain, which just depends on R2 over R1 ratio. All right, let's keep this as equation 1. Now what I'm going to do is I'm going to focus the rest of the circuit. So we got to this point VA. Now I need to deal with the last op-amp, which effectively implements the last portion of the Sallen-Key, in this case a low-pass filter, because of the way the arrangement for caps. If the frequency goes super high, then the caps large enough, basically, the caps will short. When the caps short, they will force the voltage at the positive terminal to go to AC ground. A negative also will be going to AC ground because of virtual short, as long as this op-amp 3 is operating properly, and that would force output to 0. So high enough frequency, these caps will short, and effectively this final stage will be killing the output voltage. So effectively high enough frequencies are not passing, so it's a low pass filter. It's a Sallen-Key topology. So what we can do is we can just, and let me just change the color so that you also see naming. I'm going to name this node as VB, and I'm going to name this node as V. So here's VB, and this node is as simple as just a voltage division between these components and V out. So what is this node? Well, for this node, I can simply say it is R3. So whatever that node is R3 divided by R3 again, plus, since ideal op-amp does not has infinite input impedance, no current go in or go out from the negative terminal, so effectively this is in series with R3, so we get K minus 1 times R3. So you can see that interesting, the whole thing goes away and it becomes of course times V out. The whole thing becomes V out divided by K. So the nice thing is, therefore, I'm going to write this node as V out over K, where K is this parameter, that is the parameter of this variable resistor, or resistor that you can set it once. So this can be a potentiometer or something that you set once. Okay, so we got V out over K. Let's keep that. Now, this, because of virtual short, positive, negative input terminals of op-amp 3 should be the same. So this node should be V out over K as well. That's great. Okay, so the last thing I need to do to solve the whole problem is just write one simple KCL, or Kirchhoff current law here, which says the current that is flowing inward, say in this case, this current, which is simply VA minus VB over the resistor R1, this resistor, should be equal to the current that is flowing, let's say, through R1 here, and also current that is flowing through this gap. So that's the Kirchhoff current law. The sum of currents flowing in and out of a node in a circuit, in this case in this node, should be 0. Okay, so using KCL at, let's say, node that has a voltage VB, says that VA minus VB divided by R1, so VA minus VB divided by R1 should be equal to, that's this current, should be equal to two other currents. So one of them is VB minus V out over K, so VB minus V out over K, and then divide by R1 as well. That's the current going through this resistor. And finally, I have this current, which is VB minus V out. So VB minus V out divide by 1 over CS. I'm talking about S-domain analysis. So the current the current is computed like this because the impedance of cap is 1 over CS. Now, if we multiply both sides of this equation with R1, it gives us this interesting simple situation. VA is 2 times VB minus V out over K times plus R1 CS times VB minus V out. Now the last, so let's keep this as equation 2. Now the interesting thing is there is a simple relationship between, let me change the color. So there is a simple relationship between VB and VOK, given that there is no current that can flow in or out of so there is no current that can go or come out of the positive terminal of ideal op-amp because it has infinite impedance. So whatever current is flowing, that current should continue flowing through this cap. So effectively VOK and VB is just a voltage division between series of R1 and C. So that makes life easy in terms of computation of the VOK as a function of VB and vice versa. So I can say, I'm going to write it here. I can say VO over K, which is the voltage at positive terminal of op-amp number 3, is equal to 1 over CS, that's the impedance of cap in series with R1, times the VB. So that's just the voltage division. Okay, so when we simplify the whole thing, it becomes as simple as, so therefore, I get this outcome, that as simple as this one, I get VB is 1 plus R1 CS divided by K times V out. So what is the significance of this? Well, the significance of this number 3 is I can substitute using equation 3 in equation 2 by substituting whenever I see VB, just use that and substitute VB with some scale of V out. So let's do that. I am going to use 2 and 3, and therefore I can say VA, and actually, you know what, I can just substitute 1, 2, 3. So instead of VA, I can also use the result from 1. So therefore, I can say negative 1 plus R2 over R1 times Vn is equal to 2 times VB, which is 2 over K. I'm substituting for VB using equation 3. 1 plus R1 CS times V out. I'm going to factor out V out. And then minus 1 over K. Again, factor out V out. And I have plus R1 CS. Okay. And then another VB, which is, let me put it this way so that it looks nice. So it will be as simple as, let's say, factor out K, and after we factor out K, we get 1 plus R1 CS minus K, finally V out. So what is the nice benefit of this? Let me go back to my original color so that it's not too much color. Okay, so the nice thing is I factored out everything. I can multiply both sides with k, and as a result, I get this. Move V in here below V out, so I get the transfer function. So overall transfer function, or H of S, which is V out over V in, becomes as simple as, minus 1 plus, let's say minus k, 1 plus R2 over R1, so R2 over R1, okay, so that's the numerator, and then we have effectively 1, because 2 minus 1 becomes 1, and then we have on this side we have, let's see, 2R1CS, and then 2 minus, let's see, let's make sure I'm not missing something. So we get 3 minus K R1CS, and finally, to simplify everything, we get all right, so we get the final component, which is basically R1 squared, C squared, S squared. So that's the overall transfer function that is beautifully showing the result of this as a function of the ratio of R2 over R1, and also the parameter K, which is the ratio of, which is related to the value of these resistors. So now, what can we say about this circuit? Well, the nice thing is, with this transfer function, we proved that we showed the final relationship between the output voltage as a function of the input voltage in a differential fashion, which involved the gain that is controllable using the ratio K and 1 plus R2 over R1, and then in denominator, we have a second order polynomial in S, which, if now interested, we can compute, say, the poles of the denominator, or we can just do it this way. Let's say I can form H of j omega by setting S equal to j omega for sinusoidal steady state analysis. So it becomes V out over V in, and if we do that, you can see that the transfer function become negative K, so negative K 1 plus R2 over R1 in numerator, and then in denominator I have 1 plus, this portion becomes negative, so 1 minus R1 C2, so R1 squared C squared omega squared, and the other part is plus J 3 minus K and R1C omega. So it's very interesting because this can effectively forms a low-pass filter in which we can set the value of R1 and C and K properly to find the proper location of the pole for this low-pass filter, and therefore define the magnitude Bode plot exactly as we want. If somebody is interested to find the poles, we would say the roots of denominator, which is a second order polynomial S, is equal to negative, so it becomes effectively something like this: K minus 3 R1 CS, and then we have plus minus, so there is, let me put it this way, okay, so we get K minus 3 R1 CS plus minus, and then we get 3 minus K squared R1 squared C squared, which we can factor out from the other one. So let's write it this way immediately. So R1C 3 minus k squared, and then we have minus 4 divided by 2 R1 squared C squared. So in this case, it becomes as simple as the pole. So we are finding poles effectively of the system. So to find the poles of system, it becomes as simple as just 1 over 2 R1C times, let's say, k minus 3 plus minus square root of, and then just you have as simple as this. It becomes 3 minus k squared minus 4, which is 3 minus k minus 2, which means 1 minus k, and then 3 minus k plus 2, which becomes 5 minus k. So depends on what we set for the value of, let's say, k in this system to find the proper poles of this design. So everything goes back there. If we set, let's say, k equal to 2, if k is 2, for example, in which the output resistor are matching effectively, then we can properly find the value of the pole. In this case, S is j omega, so we're talking about omega. So this would, you can find basically omega for this system, and from omega, so this define omega, and from omega you can set omega equal to 2 pi f, so you can find basically effectively the let's say the cutoff frequency of this low pass filter. And the format of the filter in terms of the magnitude Bode plot, so 20 log, let's say 10 magnitude of h of j omega, or h of omega as a function of omega, definitely looks something like this. So there are 2 poles in this system, so effectively at the end we'll end up with 40 dB per decade drop after the cutoff point. So there would be a cutoff frequency, let's say omega c, and from omega c we can, after that point, we can roughly say that the magnitude is dropping by 20 dB every 10 times increase of frequency, and this is effectively a low pass filter in which the overall for the portion that it passes, frequency range 0 to omega c, it has a gain, and that gain is defined by the numerator of this transfer function as shown, because when s is 0, which means dc, these components go away, and denominator effectively becomes just 1, and therefore the whole gain of system is k times 1 plus R2 over R1. I hope that this example is helpful in terms of showing how we can design such a system that is a cascade of a differential amplifier and a Sallen-Key filter, and then how we can analyze, or let's say properly select the components in the filter.